Hello there and welcome to Zero Drift, your peaceful passage through the universe. Tonight, we are going to explore one of the most quietly astonishing moments in the history of mathematics. A moment when a problem that had defeated the greatest mathematical minds in Europe for nearly a century was solved by a young man of 28, using a method so bold and so unexpected that his contemporaries could barely believe it was legitimate. And yet the answer was so perfectly beautiful that it could not possibly be wrong. This is the story of the Basel Problem. It is the story of infinite sums, of what happens when you add up not just 100 numbers or 1,000, but infinitely many, one after another, forever. It is the story of a 14th century French scholar who proved, with elegant geometric reasoning, that a seemingly gentle series of fractions never settles down to a fixed value. It is the story of two brilliant and fiercely competitive Swiss brothers who identified a problem they could not solve and challenged the mathematical world to solve it for them. And it is the story of Leonard Euler, perhaps the greatest mathematician who ever lived, who sat down with an infinite polynomial and a sine wave, and pulled from them a result so unexpected that it feels, even now, like a conjuring trick. The answer, when it came, connected two things that had no obvious reason to be connected. The sum of an infinite series of fractions, 1 plus a quarter plus a ninth plus a 16th, each term the reciprocal of a perfect square, turned out to equal exactly pi squared divided by 6. Pi, the ratio of a circle's circumference to its diameter. What on earth does a circle have to do with square numbers and their reciprocals? Nothing, it seems. And yet they are connected, deeply and necessarily, by the mathematics of infinite series and the audacious intuition of Leonard Euler. So settle in, let your body grow heavy and still, let your breathing find its own slow rhythm. And allow the story of the Basel problem, of infinity tamed, of pi found in the most unexpected place, of mathematical beauty revealed through centuries of patient and brilliant effort, to carry you gently towards sleep. Before we can appreciate the Basel problem, we need to understand something more fundamental, the idea of an infinite sum, and the question of whether such a thing can have a finite value. Our intuition about addition comes from the finite world. You add two numbers and you get a third. You add 100 numbers and you get their sum. The process terminates, and the result is a specific, definite number. But what happens when the list of numbers you are adding never ends? What happens when there is always another term to add, and another after that, stretching out forever into the mathematical horizon? The answer, it turns out, depends entirely on the terms you are adding. Some infinite sums grow without bound. You can add as many terms as you like, and the total will keep increasing, never settling down to a fixed value. We say such sums diverge. Other infinite sums, remarkably, do settle down. The running total approaches a specific number more and more closely as you add more and more terms, and in the limit of infinitely many terms, the total equals that number exactly. We say such sums converge. The distinction between convergence and divergence is one of the most fundamental in all of mathematics, and learning to tell the two apart and to calculate the exact value when a sum converges occupied some of the greatest minds in history. Let us begin with the simplest possible infinite sum. What happens when you add all the positive integers, 1, 2, 3, 4, 5, all the way to infinity? The answer is obvious, really. The sum grows without bound. Each term is larger than the previous one, and the total increases without limit. The sum of all the positive integers diverges to infinity. This much is clear, but now something more subtle. What happens when, instead of adding larger and larger numbers, you add smaller and smaller ones? What if you add the reciprocals of the positive integers, 1 plus a half, plus a third, plus a quarter, plus a fifth, on and on forever? Each term is smaller than the last. The terms are shrinking towards zero. Surely the total must eventually settle down to some fixed value. This is the harmonic series, and the answer is one of the great surprises in mathematics. Despite the fact that its terms get smaller and smaller, approaching zero, the harmonic series diverges. It does not converge to a finite value. Given enough terms, the sum will exceed any number you name, 1,000, 1,000,000, 1,000,000,000,000, though it takes an extraordinarily long time. To exceed 10, you need more than 12,000 terms. To exceed 20, you need more than 250 million. The proof that the harmonic series diverges was given, in its most beautiful form, by a 14th century French scholar named Nicole Orsmy. Orsmy was a remarkable figure, a philosopher, theologian, economist, and mathematician who worked in Paris in the 1360s and 70s, and whose mathematical insights were centuries ahead of their time. He would not be widely recognized for this contribution for hundreds of years, but his argument for the divergence of the harmonic series remains one of the most elegant proofs in mathematical history. Orsmy's argument is beautifully simple. He grouped the terms of the harmonic series in a specific way. The first group contained just the number 1. The second group contained a half. The third group contained the third and the fourth, 2 terms. The fourth group contained the fifth through the 8th, 4 terms. The fifth group contained the 9th through the 16th, 8 terms. Each group contained twice as many terms as the previous one. Then he estimated the sum of each group from below. The third group, a third plus a quarter, is greater than a quarter plus a quarter, which equals a half. The fourth group, a fifth through an 8th, has 4 terms, each at least as large as an 8th, so the group sum is at least 4 times an 8th, which again equals a half. The fifth group has 8 terms, each at least a 16th, so again the group sum is at least a half. Every group, Orsmy argued, contributes at least a half to the total. And since there are infinitely many groups, the total must exceed a half added to itself infinitely many times, which is infinite. The harmonic series diverges. The proof is complete. Drift a little deeper now. The night is quiet and the story of infinite sums is just beginning to reveal its surprises. We have seen a sum that converges, any finite sum, obviously, and 2 that diverge. The natural question is whether any infinite sum of positive terms can converge to a finite value. And the answer is yes, as we are about to see. In the early 1670s, in Paris, a young German diplomat named Gottfried Wilhelm Leibniz crossed paths with the Dutch mathematician and physicist Christian Huygens, and the meeting changed the course of his life, and through him, the course of mathematics. Leibniz was not, at that point, primarily a mathematician. He was a philosopher and a diplomat, educated in law and philosophy, possessed of a remarkable breadth of intellectual interests, and an almost supernatural ability to master whatever he turned his attention to. He had entered the University of Leipzig at the age of 15, completed his doctorate at 20, and was working as a diplomatic representative of a German prince when he arrived in Paris and encountered Huygens. Huygens recognized Leibniz's exceptional ability immediately and became an informal mentor to the young German, introducing him to the frontiers of contemporary mathematics and physics. Among the problems Huygens posed to Leibniz was one that seemed, on the surface, quite innocent. What is the sum of the reciprocals of the triangular numbers? The triangular numbers are the numbers you get by adding consecutive integers starting from 1. The first triangular number is 1. The second is 1 plus 2, which is 3. The third is 1 plus 2 plus 3, which is 6. The fourth is 10. The fifth is 15. The sixth is 21. They are called triangular because they can be visualized as triangles of dots, 1 dot in the first row, 2 in the second, 3 in the third, and so on, with the total number of dots in each triangle being a triangular number. Huygens wanted to know what happens when you take the reciprocals of all these triangular numbers and add them up forever. The sum of 1 plus a third plus a sixth plus a 10th plus a 15th, on and on, infinitely. Does this series converge? And if so, to what? Leibniz solved this problem with an insight that has become one of the classic examples of mathematical elegance. He noticed that each term in the series could be rewritten using a telescoping trick. The reciprocal of the nth triangular number is 2 divided by n times n plus 1. And this can be written as 2 times the quantity 1 over n minus 1 over n plus 1, When you write it this way and add up all the terms, something remarkable happens. Most of the terms cancel. The -1/2 from the first term cancels the +1/2 from the second. The -1/3 cancels the +1/3 from the third. And so on, down the entire infinite chain. What remains is only the very first positive term, 2 times 1, which is 2. The sum of the reciprocals of all the triangular numbers is exactly 2. This was a triumph. Leibniz had not merely shown that the series converged, he had found its exact value, not an approximation, not a numerical estimate, but a clean, beautiful, integer result. 2. The entire infinite series summed to exactly 2. And once you have one example of an infinite series converging to an exact value, the questions multiply immediately. If the triangular reciprocals sum to 2, what do the square reciprocals sum to? What is the value of 1 plus a quarter plus a ninth plus a 16th? The reciprocals of the perfect squares added up forever. This was the question that would become known as the Basel Problem. Let your eyelids grow heavier as the story moves forward to the Bernoulli brothers, two of the most gifted and most quarrelsome mathematicians of the late 17th century, whose rivalry and obsession with infinite series set the stage for Euler's triumphant solution. Jacob Bernoulli was born in Basel, Switzerland, in 1654. His younger brother Johann was born in 1667. Both were mathematical prodigies, and both were deeply influenced by the work of Leibniz, whose calculus they learned independently and whose ideas they championed, promoted, and developed with enormous creativity. Together and separately, they made fundamental contributions to calculus, probability theory, and the theory of differential equations. They were, by any measure, among the greatest mathematicians of their generation. They were also famously bitter rivals. The relationship between Jacob and Johann combined genuine intellectual closeness with personal antagonism that could be fierce and sometimes petty. They competed for priority, disputed credit, and occasionally published attacks on each other's work that were more personal than mathematical. The rivalry was partly a product of the times, an era when scientific priority was fiercely contested and credit could make or break a reputation, and partly a product of their personalities. Both were proud, both were competitive, and both knew that the other was very nearly their equal. What brought them together, intellectually, was a shared obsession with infinite series. Both brothers proved independently that the harmonic series diverges. Johann's proof was particularly elegant, building directly on Leibniz's work on triangular numbers. And both turned their attention to the reciprocal square series, 1 plus a quarter plus a ninth plus a 16th, and found themselves unable to determine what it summed to. Jacob made the most significant progress. He was able to show, using a comparison with the triangular number series that Leibniz had solved, that the reciprocal square series converged to some finite value. His argument was as follows: the nth square number is n squared. The nth triangular number is n times n plus 1 divided by 2, and n squared is always at least as large as n times n plus 1 divided by 2 for n at least 2, which means the reciprocal of n squared is at most the reciprocal of the nth triangular number. Since the sum of the triangular reciprocals converges to 2, and the square reciprocals are all at most as large as the triangular reciprocals, the square reciprocal sum must also converge, and must be at most 2. This was progress. Jacob had shown the series converged to a value less than 2. Numerical calculation suggested the value was somewhere around 1.64, but what was it exactly? No pattern emerged from the calculations. No clever trick suggested itself. The series converged, but to what? Jacob was honest enough to admit defeat publicly, writing in a treatise that if anyone could find the exact sum, great would be his gratitude. The challenge echoed across European mathematics. The best minds of the early 18th century tried and failed to crack it. The problem became known as the Basel Problem after the Swiss city where the Bernoulli brothers had worked, and it remained open, tantalizing, and apparently impenetrable until a young man from Basel, once a student of Johann Bernoulli himself, arrived on the scene and changed everything. Leonard Euler was born in Basel, Switzerland, in 1707, the son of a Protestant minister with mathematical interests. From an early age, his gifts were extraordinary, not the modest precocity of a clever child, but the deep, comprehensive mathematical brilliance that appears perhaps once in a generation. His father, recognizing what he had, arranged for the young Euler to study privately with Johann Bernoulli, who was by then the most prominent mathematician in Switzerland. Johann Bernoulli was not an easy man. He was proud, competitive, and could be difficult with students who failed to meet his standards. But Euler met his standards and exceeded them, and Bernoulli quickly recognized that his pupil was something exceptional. They worked together closely for several years, and when Euler left Basel for a position at the newly founded St. Petersburg Academy in Russia at the age of 20, he carried with him not only Bernoulli's mathematics, but a deep familiarity with the unsolved problems of the age, including the Basel problem that had defeated Johann's brother Jakob years before. Euler's career was defined by two qualities above all others: prodigious mathematical output and the capacity for genuine, transformative insight. He was extraordinarily prolific. His collected works run to more than 70 volumes, and he continued to produce mathematics at a remarkable rate even after losing his sight completely in his late 50s. He worked by dictating his results to assistants, holding the full machinery of his calculations in his extraordinary memory. When asked how he could continue to work in total darkness, he reportedly said that he found it actually easier. There were fewer distractions. But it was not the volume of Euler's output that made him unique. It was the quality of his intuition, the ability to see connections between areas of mathematics that seemed completely unrelated, to make leaps that were, strictly speaking, not rigorous, but that pointed so clearly toward deep truth that the rigorous proof would inevitably follow. The solution of the Basel problem was the first great demonstration of this quality, and it made Euler famous across Europe at the age of 28. The key to Euler's approach was the sine function. You know the sine function, at least by name. It is the fundamental oscillating function of trigonometry, the function that describes, among many other things, the height of a point on a rotating wheel, the displacement of a vibrating string, the amplitude of an electromagnetic wave. Its graph is a smooth, undulating wave that oscillates between +1 and -1, crossing zero at regular intervals separated by pi radians. The zeros of the sine function are the values of x for which sine of x equals 0. These occur at x equals 0 and at x equals plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, at every integer multiple of pi, positive and negative. This is a fundamental property of the sine function that Euler knew perfectly well. Euler also knew something that was, in the early 18th century, relatively recent and extraordinarily powerful. Any smooth function can be expressed as an infinite polynomial, an infinite sum of powers of x, with specific coefficients determined by the function's derivatives. This representation is called the Taylor series, named for Brooke-Taylor, though the idea had been developed independently by several mathematicians in the late 17th and early 18th centuries. The Taylor series of the sine function is particularly clean, because the sine function has a specific pattern of derivatives: sine, cosine, negative cosine, and then the cycle repeats. The Taylor coefficients follow a simple pattern. The result is that sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, an alternating series of odd powers of x, with denominators given by factorials of odd numbers. This is an exact representation, not an approximation, but an identity that holds for all values of x. The infinite polynomial on the right is exactly the sine function. Now, Euler considered the function sine of x divided by x. He noticed that this function, unlike sine of x itself, equals 1 when x equals 0, because sine of x approaches x for small x, so the ratio approaches 1. And the zeros of sine of x divided by x are the same as the zeros of sine of x, excluding x equals 0, namely plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, and so on. Armed with this observation, Euler made a bold and, strictly speaking, not fully justified move. He argued that since finite polynomials can be written as products involving their roots, perhaps infinite polynomials could be too. A polynomial with roots at the values r1, r2, r3, satisfying the condition that its value at 0 is 1, can be written as a product of terms of the form 1 minus x over r. Perhaps the same was true for sine of x divided by x, with its infinitely many roots. Writing the factored form of sine of x divided by x, with roots at plus or minus pi, plus or minus 2 pi, plus or minus 3 pi, Euler obtained an infinite product. Each pair of roots, plus n pi and minus n pi, contributed a factor of 1 minus x squared over n squared pi squared. The full infinite product was therefore the product over all positive integers, n of the quantity 1 minus x squared over n squared pi squared. This was audacious. The step from finite polynomials to infinite polynomials was not rigorous. Euler was working by analogy, by intuition, by the conviction that a technique that worked for finite degrees ought to extend to the infinite case. It was exactly the kind of non-rigorous but inspired leap that characterized his best work. And then he compared the two representations of sine of x divided by x on one hand. The Taylor series gave him 1 minus x squared over 6 plus higher powers. On the other hand, the infinite product, when expanded, gave him 1 plus a coefficient times x squared plus higher powers. The coefficient of x squared in the infinite product expansion was the negative of the sum of 1 over n squared pi squared over all positive integers, n matching the two expressions for the coefficient of x squared. The Taylor series coefficient was negative 1/6, and the product coefficient was negative 1 over pi squared times the sum of 1 over n squared. Euler found that 1/6 equals 1 over pi squared times the sum of the reciprocals of the square numbers. Rearranging, the sum of the reciprocals of the square numbers equals pi squared over 6. The Basel problem was solved. As you rest in the deepening quiet of this night, let the result wash over you, pi squared over 6. The sum of 1 plus a quarter plus a ninth plus a 16th, added up forever through all the square numbers to infinity, equals pi squared over 6. Approximately 1.6449. Pi, the number that describes circles, the ratio of the circumference of a circle to its diameter. A number that has been calculated and studied since antiquity, that appears in the formula for the area of a circle and the volume of a sphere, that shows up in probability theory and quantum mechanics and the distribution of prime numbers. What possible connection could pi have with the sum of the reciprocals of the square numbers? None that is visible from the outside. None that you would predict or even suspect before seeing the proof. The connection is not superficial. It is not a coincidence or an approximation or a numerical curiosity. It is a deep mathematical identity, provably exact, necessarily true in any mathematical universe in which the sine function and the integers both exist. This is one of the most remarkable features of mathematics, the way deep connections appear between quantities that seem to have nothing to do with each other. Pi was discovered through the geometry of circles. The square numbers were discovered through the process of squaring integers. There is no obvious reason why these two things should be related, and yet the connection is real and beautiful, and the proof of its reality is one of the crowning achievements of 18th century mathematics. When Euler announced his result in 1735, at the age of 28, it caused a sensation. The Basel problem had been open for nearly 50 years. The Bernoulli brothers had failed to solve it. Leibniz had failed to solve it. The best mathematicians in Europe had failed to solve it. And Euler had solved it not just by finding the value, but by finding it through a method of such originality and such power that it immediately suggested generalizations and extensions. Daniel Bernoulli, son of Johann, another gifted mathematician in a family seemingly overflowing with them, wrote that Euler's solution had shed new light on the entire subject of infinite series. Other mathematicians, initially skeptical of the non-rigorous step involving infinite products, were won over by the beauty of the result and by subsequent verifications that confirmed its correctness. The method was eventually made fully rigorous, justifying Euler's intuition from solid mathematical foundations. Euler did not stop with the square numbers. The method he had used, comparing the Taylor series expansion of sine of x divided by x with the infinite product expansion, generalized immediately to higher powers. He computed the sum of the reciprocals of the fourth powers and found that it equaled pi to the fourth over 90. The sum of the reciprocals of the sixth powers equaled pi to the sixth over 945. The sum of the reciprocals of the eighth powers involved pi to the eighth. The pattern extended to all even powers, each time yielding pi to the corresponding even power divided by some specific integer. These results constitute what is now called Euler's formula for the values of the Riemann zeta function at even positive integers. The Riemann zeta function, denoted zeta of s, is the function that takes a number s and returns the sum of the reciprocals of the integers raised to the power s. The Basel problem asked for the value of zeta at s equals 2, which Euler showed was pi squared over 6. His generalizations gave the values at all even positive integers. For the even integers, the pattern is complete. Each value is a rational multiple of the corresponding power of pi, clean, explicit, and computable. Euler computed these values by hand up to zeta at 26, a staggering achievement in an era before calculating machines. But the odd powers tell a completely different story. What is the sum of the reciprocals of the cubes, 1 plus an eighth plus a 27th plus a 64th, forever? This is zeta at 3, sometimes called Apéry's constant after the French mathematician Roger Apéry, who proved in 1978 that it was irrational. But no one has found a formula for it in terms of pi or any other familiar mathematical constant. What is zeta at 5? At 7? At 9? These are among the deepest unsolved mysteries in mathematics. The contrast is striking and somewhat mysterious. The even power zeta values are beautifully explicit, all expressible in terms of pi. The odd power zeta values are shrouded in darkness. No formula is known. No pattern has been identified that would allow us to say what zeta at 3 or 5 or 7 equals in terms of familiar quantities. The odd values seem to be genuinely new mathematical constants, not reducible to anything we already know. Why the distinction between even and odd powers? The answer lies in the deep structure of the zeta function and its relationship to the symmetry of the complex plane, a relationship that Riemann understood in 1859 when he wrote his famous 8-page paper extending the zeta function to complex numbers and making the conjecture that bears his name. But the full reason for the even-odd distinction and the question of whether the odd zeta values are related to each other or to pi in some way not yet discovered remains one of the great open questions in number theory. The Riemann zeta function deserves a moment of attention here because it is the mathematical object that connects the Basel problem to the deepest unsolved question in mathematics. Bernhard Riemann was a German mathematician of the middle 19th century, a student of the great Carl Friedrich Gauss, who made fundamental contributions to geometry, complex analysis, and number theory in a career cut short by tuberculosis at the age of 39. His most celebrated contribution was the 8-page paper of 1859 on the number of primes less than a given magnitude, in which he extended the zeta function, Euler's sum of reciprocal powers, from the real numbers to the complex plane, and identified a deep connection between the zeros of the extended function and the distribution of prime numbers. Riemann showed that the zeros of the complex zeta function the values of the complex variable s, for which zeta of s equals 0, are intimately connected to the pattern of prime numbers along the number line. The more we know about where the zeros are, the more we know about how the primes are distributed. Riemann conjectured that all the non-trivial zeros of the zeta function, all the zeros, except the obvious ones at the negative even integers, lie on a specific vertical line in the complex plane, the line where the real part of s equals 1/2. This conjecture is the Riemann hypothesis. The Riemann hypothesis has been verified computationally for more than 10 trillion zeros, every one of them on the critical line, exactly where Riemann conjectured. But it has not been proved for all zeros, and despite the efforts of the greatest mathematical minds of the past century and a half, a proof remains elusive. The Clay Mathematics Institute has offered a prize of $1 million for a proof or disproof. The problem remains open. The Basel problem, the elementary question about the sum of reciprocal squares that the Bernoulli brothers could not solve, sits at the very entrance to this vast mathematical edifice. The answer, pi²/6, is the value of the Riemann zeta function at the integer 2. Euler's method for computing it was the first step toward understanding the zeta function as a mathematical object of fundamental importance. And the deep mysteries of the zeta function, its zeros, its values at odd integers, its connection to the prime numbers, are all descendants of the question Euler answered so triumphantly in 1735. From a boy pairing numbers in school to a 14th century scholar grouping fractions, from two quarrelsome Swiss brothers to a young genius in St. Petersburg, the story of the Basel problem is a story about mathematical generations, each one building on the last, each one pushing a little further into the unknown, each one passing the torch to the next. Let the night hold you gently as the story finds its deepest layer, the philosophical dimension of what Euler did and what it means. Euler's proof of the Basel problem is often described as non-rigorous, and in a strict technical sense, this is accurate. The step in which he treated the infinite polynomial sign of x divided by x as if it could be factored into its roots in the same way as a finite polynomial was not, at the time, supported by any theorem justifying such a move for infinite products. The rigorous justification, the Weierstrass factorization theorem, which establishes conditions under which entire functions can be expressed as infinite products over their zeros, was not developed until the late 19th century, but calling Euler's proof non-rigorous misses something important. Euler was not being careless, he was being bold. He was applying a technique that worked for finite polynomials to an infinite one, on the grounds that there was no reason it should not work and that the result was testable. He could check his answer numerically, and the numerical check confirmed it. He could generalize the method to higher powers and obtain answers that could also be checked. The method was consistent, productive, and pointed toward truth even before it could be made fully rigorous. This is one of the ways that mathematics actually progresses, not always by starting from axioms and deriving conclusions through unbroken chains of rigorous logic, but sometimes by leaping ahead on intuition and then going back to provide the foundations. The intuition comes first, followed by the rigorous justification that establishes the truth of what the intuition perceived. Euler's Basel proof followed exactly this pattern, and it is one of the finest examples in mathematical history of what Henri Poincaré called the mathematical instinct, the ability to sense, before the proof is available, that something is true. The answer itself, pi²/6, is also a reminder of one of the deepest and most discussed features of mathematics, its unreasonable effectiveness in describing reality and the unexpected connections that appear between quantities that seem to have no relationship. Pi, discovered through the geometry of circles, appears in the sum of reciprocal squares. The Bernoulli numbers, discovered through the study of sums of powers, appear in the values of the zeta function at even integers. The prime numbers, the most elementary objects in arithmetic, are governed by the zeros of the complex zeta function. These connections are not accidents. They are evidence that the mathematical universe has a coherence and a unity, that the different areas of mathematics, which appear from the outside to be separate disciplines with separate concerns, are in fact aspects of a single underlying structure, connected by threads that become visible only when you look at them from the right angle, with the right tools, with the patience and the boldness to follow the mathematics wherever it leads. Euler followed the mathematics boldly and with extraordinary intuition, and what he found when he arrived was pi, hidden in a sum of fractions, waiting to be discovered by someone willing to see it. There is something worth pausing over in the biography of Leonard Euler that speaks to the human dimension of this story, the character of the man behind the mathematics, and what his life tells us about the nature of mathematical genius. Euler was, by all accounts, a man of remarkable equanimity. He was sociable and warm, a devoted family man who fathered 13 children, of whom 5 survived to adulthood. He was genuinely pious, in the Lutheran tradition in which he had been raised, and saw no conflict between his faith and his mathematics. Both, for him, were ways of exploring the order and rationality of a creation he believed to be fundamentally ordered. He was kind to his students and generous with his time and ideas in an era when scientific credit was fiercely contested. He was also, as noted, almost impossibly prolific. Even the loss of sight in his right eye at age 31, the result of a fever and a loss he bore with characteristic stoicism, did not slow his output. When he lost sight in his remaining eye at the age of 59, he simply dictated his results to assistants and continued working at essentially the same pace. In the last 17 years of his life, working in complete darkness, Euler produced roughly half of his total mathematical output. The ability to hold complex mathematical structures in memory, to manipulate them mentally without the aid of pencil and paper, to find results and verify them, and communicate them through dictation. This was either a product of extraordinary natural gifts or of decades of mathematical practice, or most likely both. Euler died in St. Petersburg in 1783 at the age of 76. According to the account of the mathematician Nicholas Fuss, Euler spent the afternoon of the day he died doing calculations concerning the recent discovery of the planet Uranus, then had dinner with his family, then suffered a stroke and died within a few hours. The mathematician Condorcet wrote in an obituary that Euler ceased to calculate and to live in the same moment. The image is both poignant and somehow fitting. Euler's life was, in a very real sense, calculation, not the dry, mechanical calculation of a computing machine, but the creative, intuitive, expansive calculation of a mathematical mind of the first order. To cease to calculate was to cease to be Euler, and it is almost impossible to imagine him continuing to exist without mathematics. His mathematical legacy is almost without parallel in the history of the subject. He introduced or standardized most of the notation that modern mathematics uses: the letter E for the base of the natural logarithm, the letter I for the square root of -1, the Greek letter sigma for summation, f of x for the value of a function, and many others. He made fundamental contributions to every branch of mathematics that existed in his time and created several new ones. The formula that bears his name, e to the power of I pi equals -1, is routinely voted the most beautiful equation in mathematics, combining 5 of the most fundamental constants in a single identity of breathtaking economy. And it was Euler who solved the Basel problem at 28, with a proof so bold and so beautiful that it remains one of the most celebrated results in mathematical history. The harmonic series with which this story began has a poetic relationship to the Basel problem that is worth noticing. Both series involve the positive integers. The harmonic series takes the integers and forms their reciprocals: 1, a half, a third, a quarter. The reciprocal square series takes the integers, squares them, and then forms the reciprocals 1, a quarter, a ninth, a 16th. The harmonic series diverges slowly, agonizingly slowly, but without bound. The reciprocal square series converges to pi squared over 6. What makes the difference? The squaring. The act of squaring each integer before taking the reciprocal makes the terms small enough, fast enough, that they can be summed to a finite value. This connects to a general principle in the theory of infinite series. The series of the reciprocals of n to the power s converges if s is greater than 1 and diverges if s is less than or equal to 1. At s equals 1, you have the harmonic series divergent. At s equals 2, you have the reciprocal squares convergent, summing to pi squared over 6. The threshold between convergence and divergence is at s equals 1, and the zeta function maps out how the sum behaves on both sides of that threshold. This is the subject of analytic number theory, the study of the distribution of prime numbers using the tools of mathematical analysis, and the zeta function is its central object. Euler's Basel calculation, viewed from this perspective, was not merely the solution of an isolated puzzle. It was the first step in the development of one of the most powerful and most active areas of modern mathematics. The connection between the Basel problem and pi carries a special kind of wonder, not the wonder of surprise, exactly, because mathematicians have long since become accustomed to pi appearing in unexpected places, but the wonder of depth, the wonder of a universe that turns out to be more interconnected than we had any reason to expect. Pi appears in the formula for the area of a circle. It appears in the probability that two randomly chosen integers have no common factor. It appears in the formula for the sum of reciprocal squares. It appears in the formula for the volume of a sphere in any number of dimensions. It appears in quantum mechanics, in statistical mechanics, in the theory of prime numbers. It appears, in some form or another, in essentially every branch of mathematics and mathematical physics. Why? Is there a deep reason why pi, the ratio of a circle's circumference to its diameter, the most fundamental constant of Euclidean geometry, appears so pervasively in contexts that seem to have nothing to do with circles? The answer lies in the deep relationship between the exponential function and the trigonometric functions, a relationship captured in Euler's formula that e to the power of I times x equals cosine of x plus I times sine of x. This identity connects the geometry of circles, encoded in the cosine and sine functions, with the arithmetic of exponential growth, encoded in the exponential function. And because exponential functions appear everywhere in mathematics, and because their connection to trigonometry brings pi along wherever they go, pi is ubiquitous. The reciprocal square series sums to pi squared over 6 because the sine function, which is fundamentally circular, fundamentally about angles and pi, appears in the most natural infinite polynomial representation of the sum. Euler found pi in the square reciprocals because the sine function, with its circular essence, was lurking in the background of the calculation, waiting to reveal itself to someone perceptive enough to see it. As you drift towards sleep, let the story settle into a single, quiet image. A young man sitting at a desk in St. Petersburg in the 1730s, surrounded by papers covered in calculations. The year is 1735. Outside, it is winter. The city is cold and new and full of the energy of a young empire reaching for modernity. Inside, by candlelight, Euler is writing out the Taylor series for the sine function, comparing it with an infinite product, matching coefficients. He writes down the coefficient of x squared on one side of the equation and the coefficient of x squared on the other side. He sets them equal, he rearranges, and suddenly there it is, pi squared over 6. He checks it numerically. The decimal expansion he has been calculating, 1.6449 and beyond, matches the value of pi squared divided by 6 to more decimal places than he has computed. The match is exact, not approximately. The Basel problem is solved. He writes it down, checks it again, and then writes a note in his mathematical journal that has survived to this day. Quite unexpectedly, he records, "I have found an elegant formula depending on pi." Quite unexpectedly, a formula depending on pi. The greatest mathematician in the world, writing down one of the most beautiful results in the history of mathematics, describing it as unexpected. The genuine surprise of discovery, the real felt surprise of encountering something you did not see coming, is one of the most human of mathematical experiences, and it is moving to find Euler, with all his extraordinary powers, describing the result as unexpected. It was unexpected because pi had no obvious reason to be there. And yet there it was. And now, more than 250 years later, we know why it was there. We have the rigorous proofs, the functional equations, the infinite product representations that establish the result beyond any doubt. But Euler knew it first, by instinct, by boldness, by the particular genius that allowed him to see connections that others could not. The sum of the reciprocals of all the square numbers is pi squared over 6. It was true before Euler discovered it. It will be true forever. And tonight, having followed the story from Gauss pairing numbers in school to Osmy grouping fractions to Leibniz and his telescoping trick to the Bernoulli brothers and their failed attempts to Euler's inspired solution, you have carried this truth with you through the night. Let it rest now, quiet and permanent, in whatever corner of your awareness wants to hold it. The mathematics will still be there in the morning. The primes will still be governed by the zeta function. The odd zeta values will still be mysterious. The Riemann hypothesis will still be waiting for its proof. And pi squared over 6 will still equal 1 plus a quarter plus a ninth plus a 16th, added up forever. Some things are just true, and that is a very peaceful kind of knowledge to fall asleep with. To fully appreciate what Euler achieved in solving the Basel problem, it helps to understand the mathematical culture of the early 18th century, the world in which he was working, the problems that were considered central, and the tools that were available. The late 17th and early 18th centuries were the era of the calculus revolution. Newton in England and Leibniz in Germany had independently developed the calculus in the 1670s and 1680s, the mathematical framework for dealing with continuous change, for finding tangent lines and areas, and the rates at which quantities vary. The development of calculus was one of the most consequential events in the history of mathematics, opening up vast new areas of inquiry and providing tools of extraordinary power for both pure mathematics and natural philosophy. The immediate aftermath of the calculus revolution was a period of intense mathematical activity across Europe. Mathematicians were applying the new techniques to problems in geometry, mechanics, astronomy, and the theory of numbers. Infinite series, representations of functions as infinite sums, were a particularly active area of investigation. The Taylor series, the binomial series, and various trigonometric and logarithmic series were being developed and applied to compute values of functions to high precision. It was in this context that the Basel problem attracted such intense interest. Infinite series were the central tool of the age, and a natural infinite series that seemed to converge but whose sum could not be determined was a genuine challenge to the best available methods. The fact that the Bernoulli brothers, among the most powerful mathematical minds of their generation, had tried and failed made the problem famous. The fact that it involved square numbers, one of the most fundamental sequences in arithmetic, gave it a special status. Euler arrived in this world as a student of Johann Bernoulli, trained in the most powerful methods of the day and possessed of a mathematical intuition that exceeded anything his teacher had seen. He began working on the Basel problem while still in his 20s, first trying to compute the sum numerically to high precision through clever series transformations, and then seeking the exact value through a more fundamental approach. His numerical work was itself remarkable. In an era before calculating machines, Euler was able to compute the sum of the Basel series to 6 decimal places. a computation that required not just the first 20 or 30 terms, which converge far too slowly, but clever mathematical tricks for accelerating the convergence. He found the value 1.644934 and sat with this number, turning it over in his mind, looking for a pattern, looking for a connection to known constants. The connection to pi was not obvious from the decimal expansion alone. Pi squared over 6, computed to 6 decimal places, is 1.644934. They match. But finding this match required either a guess informed by deep intuition or a calculation that arrived at pi independently through a different route. Euler did both. He guessed that pi was involved, and then he found the calculation that confirmed it. The guess was informed by a growing awareness among early 18th century mathematicians that pi appeared in unexpected places far removed from circle geometry. The Wallis product, an infinite product formula for pi discovered by John Wallis in the 1650s, was one such appearance. The Leibniz formula for pi, 1 minus a third plus a fifth minus a seventh, the alternating sum of odd reciprocals, was another. Pi was clearly a constant of broader mathematical significance than its geometric definitions suggested, and Euler sensed that the Basel series, with its elegant structure, might be connected to it. The calculation confirmed the guess, and in doing so revealed why pi appears, because the sine function, which is the most natural function built from pi, has a Taylor expansion whose structure matches the Basel series when expanded and compared in the right way. Pi appeared in the Basel problem because pi is the natural scale of the sine function, and the sine function is the natural function to use when you want to factor an infinite polynomial through its zeros. This kind of retrospective explanation, seeing why something is true after you know that it is true, is characteristic of deep mathematical discoveries. The result was not predictable in advance, but once found, it illuminated a structure that had always been there, waiting to be seen. The Taylor series deserves a moment of deeper attention because it is one of the most beautiful and powerful ideas in mathematics, and understanding it more fully makes Euler's solution of the Basel problem even more impressive. A Taylor series is a way of representing any sufficiently smooth function as an infinite polynomial. The idea is that if you know the value of a function at a single point, and if you know all the derivatives of the function at that point, you can reconstruct the function everywhere, at least locally, and for many well-behaved functions, globally. The derivative of a function at a point captures the slope of the function at that point, how quickly it is increasing or decreasing. The second derivative captures the curvature, whether the function is bending upward or downward. The third derivative captures the rate of change of the curvature, and so on to all orders. Each successive derivative tells you something about the function's behavior that the previous derivatives did not capture. The Taylor series takes all of this information and encodes it into an infinite polynomial. The zeroth term is the function value at the point. The first term involves the first derivative. The second term involves the second derivative, divided by 2 factorial, the factor of factorial coming from the mechanics of the differentiation. The third term involves the third derivative, divided by 3 factorial, and so on. For the sine function, the situation is particularly clean because the derivatives of sine follow a simple 4-cycle. The first derivative of sine is cosine. The second derivative is negative sine. The third derivative is negative cosine. The fourth derivative is sine again, and then the cycle repeats. Evaluating at 0, sine of 0 is 0, cosine of 0 is 1, negative sine of 0 is 0, negative cosine of 0 is negative 1. The pattern is 0, 1, 0, negative 1, 0, 1, 0, negative 1. This means that only the odd terms in the Taylor series are non-zero and they alternate in sign. The first-order term is x. The third-order term is negative x cubed over 3 factorial. The fifth-order term is positive x to the fifth over 5 factorial, and so on. The result, sine of x equals x minus x cubed over 6 plus x to the fifth over 120 is exact, not an approximation, not a truncation at some finite order. The infinite series converges to sign of x for every real value of x. This is a theorem, provable from the definition of the sine function and the properties of Taylor series. The remarkable thing is that a function defined geometrically as the ratio of the opposite side to the hypotenuse of a right triangle turns out to be exactly representable as an infinite polynomial involving only integer coefficients and factorials. The geometry and the arithmetic are, it turns out, two ways of describing the same thing. The Taylor series bridges them, and Euler used that bridge to find the connection between the Basel problem and pi. It is worth pausing to appreciate the role of mathematical notation in this story, the way the language of mathematics shapes what can be thought and discovered. Euler was not just a brilliant mathematician, he was also a brilliantly effective mathematical communicator, and much of his lasting influence on mathematics came through his choices of notation. The symbols and conventions that mathematicians use today, the letter E for the base of the natural logarithm, I for the imaginary unit, f of x for a function value, sigma for a sum, pi for the ratio of circumference to diameter, were largely introduced or popularized by Euler. Good mathematical notation is not merely a matter of convenience. It shapes the way problems can be framed and solutions can be found. A well-chosen notation makes structure visible, reveals patterns, and suggests approaches that a different notation would obscure. The development of algebraic notation in the 16th and 17th centuries was essential to the development of the calculus. The development of Leibniz's notation for the calculus, dy by dx for derivatives, the integral sign for integrals, was more productive and more widely adopted than Newton's notation, partly because it made the structure of calculus more transparent. Euler's notational contributions were in the same spirit. By giving standard names to fundamental constants and operations, he made it easier to think clearly about the relationships between them. The Euler identity, e to the power of I pi plus 1 equals 0, is in part a triumph of notation. The five constants e, I pi 1 and 0 each have elegant standard symbols. The relationship between them can be expressed in a single line of beautiful mathematical writing. The Basel problem solution is similar. The notation for the sum, a sigma for the sum, then 1 over n squared, with n running from 1 to infinity, makes it immediately clear what is being asked. The answer, pi squared over 6, makes it immediately clear what has been found. Without good notation, these ideas are much harder to think about and communicate. With it, they become precise, memorable, and available for further development. Euler's mastery of notation was part of his mastery of mathematics more broadly. He saw structure clearly, he expressed it precisely, and he built on it productively. The Basel problem solution is a monument to all three of these qualities. The Basel problem exists at the intersection of several different areas of mathematics, and the story of its solution illuminates the way those areas connect and inform each other. Number theory is the study of the integers and their properties. Prime numbers, divisibility, modular arithmetic, Diophantine equations, these are the central objects and questions of number theory. The Basel problem, at its core, is a question about the integers. It asks what happens when you sum the reciprocals of the squares of all the integers. In this sense, it is a question in number theory, but the answer involves pi, which is a quantity of geometry and analysis. Pi arises from circles and from the sine and cosine functions. The connection between the integers and pi, mediated by the Basel problem, is a connection between number theory and analysis, what mathematicians call analytic number theory. Analytic number theory is the branch of mathematics that uses the tools of mathematical analysis, infinite series, functions of a complex variable, contour integration, to study the properties of integers. It is one of the most powerful and most active areas of modern mathematics. The proof of the prime number theorem, which describes the asymptotic distribution of prime numbers, is an achievement of analytic number theory. The partial progress on the Riemann hypothesis that has been made over the past century uses the tools of analytic number theory. And the foundational object of analytic number theory, the Riemann zeta function, is nothing other than the natural generalization of the Basel series. The Basel series is zeta at s equals 2. The harmonic series is zeta at s equals 1 divergent, corresponding to the pole of the zeta function. The zeta function connects these concrete, elementary questions about integer reciprocals to the deepest questions in the theory of prime numbers. Euler saw the connection between the Basel series and the zeta function, though the full development of the zeta function as a complex analytic object came later with Riemann. Euler computed the values of the zeta function at all even integers and noticed the pattern rational multiples of powers of pi. He saw that the zeta function was a meaningful mathematical object worthy of systematic study, not just a collection of isolated series. He laid the groundwork for Riemann's analytic continuation and for the entire subsequent development of analytic number theory. The Basel problem is thus not just a beautiful isolated result. It is the entry point to one of the most profound areas of mathematics, connecting the integers to analysis, the discrete to the continuous, the finite to the infinite, the elementary to the profound. One of the most moving aspects of the Basel problem story is the element of human succession, the way each generation of mathematicians received a problem from the previous generation, worked on it, made progress, and passed it on to the next. Leibniz learned about infinite series from Huygens, solved the triangular number problem, and left the Basel series as an open question. The Bernoulli brothers learned from Leibniz, proved the convergence of the Basel series, showed it was less than 2, and declared that they could not find the exact sum. Euler learned from Johann Bernoulli, absorbed everything the Bernoullis had done, and then found the solution that had eluded them. This succession, teacher to student, is one of the fundamental mechanisms of mathematical progress. Mathematics is a cumulative discipline. Each generation stands on the shoulders of the previous one, using tools that were developed before and applying them in new ways. The Bernoullis could not solve the Basel problem partly because they lacked the full machinery of infinite products and their relationship to the zeros of analytic functions, a machinery that was being developed in their time but had not yet been assembled into the form that Euler would use. Euler could solve it not just because he was more talented than the Bernoullis, though he clearly was, but because he came slightly later, had access to more developed tools, and had the particular combination of audacity and intuition that allowed him to apply those tools in a non-rigorous but productive way. The lesson is not merely biographical. It is about the nature of mathematical progress. Problems that are impossibly hard in one era become tractable in the next, as new tools are developed and new perspectives emerge. The Riemann hypothesis is impossible now, or at least no one has found a proof. Perhaps in 100 years it will seem tractable, as some mathematical development we cannot currently foresee makes the path forward clear. The Basel problem waited 60 years between Jacob Bernoulli's public acknowledgement of defeat and Euler's solution. The Riemann hypothesis has waited more than 160 years. Whoever eventually solves it will be standing on the shoulders of everyone who worked on it before Riemann himself, who formulated the hypothesis, Hadamard and de la Vallée-Poussin, who proved the prime number theorem, Hardy and Littlewood, who proved infinitely many zeros are on the critical line, and all the generations since who have pushed the understanding of the zeta function forward, slowly and patiently, without yet reaching the final summit. The story of the Basel problem is a story about mathematical patience as much as mathematical brilliance. The problem waited for the right mind at the right moment, with the right tools and the right audacity. And when Euler arrived, the problem yielded, and pi was found where no one had thought to look for it. There is something deeply comforting about the permanence of the result. Pi squared over 6 was true before Euler proved it. It was true before the Bernoulli brothers failed to prove it. It was true before Leibniz summed the triangular number series. It was true before Nicole Orsmy proved the divergence of the harmonic series. It was true before the first human being ever thought about numbers. Mathematical truth is permanent in a way that no other kind of truth is. Historical events can be reinterpreted. Scientific theories can be overturned by new evidence. But a mathematical theorem, once proved, cannot be unproved. The result stands forever, independent of any particular mind that understands it, independent of any particular culture or era that values it. The sum of the reciprocals of the square numbers is pi squared over 6. This is not a claim about how the world happens to be, contingent on the particular physical laws that govern our universe. It is a claim about the logical structure of the integers and the real numbers, a structure that would be the same in any universe in which 2 plus 2 equaled 4. The Basel problem has a unique, eternal, necessary answer, and Euler found it. This permanence is one of the things that makes mathematics beautiful in a way that goes beyond aesthetics. Mathematical beauty is not just elegance of form. It is the beauty of necessity, of results that could not be otherwise, of truths that had to be true and that were discovered rather than invented. Euler invented nothing in solving the Basel problem. He discovered that pi squared over 6 was hiding in plain sight, in the reciprocals of the square numbers, waiting for someone perceptive enough and bold enough to see it. The discovery did not change the mathematical universe. It changed our understanding of the mathematical universe, revealing a connection that was always there and that will always be there, long after every mathematician who has ever worked on it has been forgotten. That is a very peaceful kind of truth to fall asleep with tonight. Pi squared over 6. Hidden in the squares, true forever, found by a young genius in St. Petersburg by candlelight in the winter of 1735. The story of the harmonic series has a particular texture worth dwelling on, the experience of being deceived by a series that seems as though it must converge but does not. This experience of mathematical deception is one of the most instructive in all of mathematics because it teaches you to distrust intuition and to demand proof. When you first encounter the harmonic series, the intuition says it should converge. The terms are getting smaller. Each one is less than the previous one. They are approaching zero. Surely the sum must level off at some point, but it does not. The terms get smaller, but not fast enough. The series grows, agonizingly slowly, without bound. The slowness is part of what makes it deceptive. If you compute the partial sums, the sum of the first 10 terms, the first 100, the first 1,000, you see a number that grows, but grows so slowly that it seems as if it might be approaching a limit. The sum of the first 100 terms is about 5.19. The sum of the first 1,000 is about 7.49. The sum of the first 10,000 is about 9.8. The sum of the first million is about 14.4. These are large numbers of terms, and the growth seems to be slowing. But it is not. It will continue forever without stopping. To exceed 100, you need to include approximately 155 billion terms of the harmonic series. To exceed 1,000, you need a number so astronomically large that it dwarfs any scale of human experience. But eventually, given enough terms, the harmonic series exceeds any number you can name. It diverges despite all appearances to the contrary. The lesson is deep. In mathematics, the appearance of convergence is not evidence of convergence. The terms approaching zero is necessary for convergence, but not sufficient. The harmonic series has terms that approach zero. They approach zero as fast as 1 over n, and 1 over n definitely goes to zero. But this is not fast enough to make the sum finite. How fast do the terms need to shrink? Fast enough for the sum to converge depends on the specific rate of decrease. The key insight, developed in the theory of infinite series, is that terms decreasing as 1 over n to the power s lead to a convergent sum when s is greater than 1 and a divergent sum when s is less than or equal to 1. At exactly s equals 1, you have the harmonic series right at the boundary, and it diverges. At s equals 2, you have the Basel series safely above the boundary, and it converges to pi squared over 6. This boundary at s equals 1 is precisely where the Riemann zeta function has its pole, where the function blows up to infinity, corresponding to the divergence of the harmonic series. The harmonic series is not just a curiosity. It is the critical case, the boundary between two worlds, and its divergence is what makes the convergence of the Basel series non-trivial and interesting. The Bernoulli brothers deserve more attention than they sometimes receive in the popular history of mathematics, because their work on infinite series was not merely the prelude to Euler's triumph. It was genuinely important in its own right, and it set the conceptual stage for everything that followed. Jacob Bernoulli, the elder brother, was born in 1654 and died in 1705. In his 13 years of productive mathematical life, from roughly 1690 to 1705, he made fundamental contributions to probability theory. His book Ars Conjectandi, published posthumously in 1713, is one of the founding texts of the mathematical theory of probability, as well as to the theory of infinite series, the calculus of variations, and differential equations. His proof that the Basel series converged was a model of the comparison method in analysis. By finding a convergent series, the Leibniz triangular number series, and showing that every term of the Basel series was at most as large as the corresponding term of the triangular series, he established convergence without knowing the sum. This is exactly the method of comparison that is taught in every calculus course today, and Jacob's application of it to the Basel series was one of its earliest and most elegant uses. His brother Johann, born in 1667, was in some respects the more talented mathematician and certainly the more combative personality. Johann Bernoulli made fundamental contributions to calculus, developed many of the rules that students learn today for computing derivatives and integrals, and was an ardent and effective advocate for Leibniz's approach to calculus against the competing approach of Newton's followers in England. He was also the teacher of Euler, and in this capacity, perhaps his most important contribution to mathematics was not any specific theorem, but the training and inspiration of the greatest mathematical mind of the 18th century. The rivalry between the brothers was famous and sometimes bitter. They disputed priority on several results, including contributions to the brachistochrone problem, the problem of finding the curve along which a ball rolls from one point to another in the least time, and their public attacks on each other were sometimes personal and intemperate. But the rivalry was also productive. Each pushed the other to greater achievements, and their combined output helped establish the Swiss mathematical tradition as one of the most productive in Europe. Both brothers failed to solve the Basel problem. This failure is as instructive as Euler's success, because it shows the limits of the methods available in their time and illuminates exactly what Euler added that they lacked. The Bernoullis had the comparison method, which established convergence. They had the Taylor series, which could represent functions as infinite polynomials, but they did not have the insight to connect the Basel series to the sine function through the infinite product representation of its zeros. That connection required the particular combination of boldness and intuition that was Euler's singular gift. Consider what Euler's result tells us about the relationship between the continuous and the discrete in mathematics, one of the deepest themes in the entire subject. The integers, the whole numbers, are the quintessential discrete objects. They are separated from each other by fixed gaps. Between 1 and 2 there is no integer. Between 1,000 and 1,001 there is no integer. The integers form a list, an isolated collection of points on the number line with nothing in between. The real numbers, by contrast, are continuous. Between any two real numbers, there is always another real number. The real line is infinitely dense, with no gaps. Continuous functions on the real line, functions like the sine and cosine and exponential, vary smoothly, without jumps or gaps, in a way that is fundamentally different from the discrete behavior of the integers. Pi is a property of the continuous world. It arises from the geometry of circles, which are the quintessential continuous objects. The circumference of a circle varies continuously as its radius varies. Pi is the ratio of the circumference to the diameter, a ratio that characterizes all circles regardless of size, a fundamental constant of the continuous geometry of the plane. The Basel series is a construction from the discrete world. It takes the integers 1, 2, 3, 4, squares them, takes the reciprocals, and adds them up. The integers, the squaring, the reciprocals, all discrete operations on discrete objects. And yet the answer is pi. The discrete world of integers connects, through the Basel series, to the continuous world of circles and geometry. The connection is exact, not approximate. The sum of the discrete series equals the continuous constant pi squared divided by 6. This connection between the discrete and the continuous is one of the deepest and most recurring themes in mathematics. The prime numbers, the most fundamental discrete objects, are connected to the continuous zeta function. The Fourier series, a representation of continuous periodic functions as infinite sums of sines and cosines, connects the continuous world of oscillation to the discrete world of integer frequencies. The relationship between the discrete and the continuous runs through all of mathematics, and the Basel problem is one of its most beautiful expressions. Euler found pi in the integers not because integers are secretly circular or continuous, but because the mathematical structures that connect the discrete to the continuous, the sine function, the infinite product, the Taylor series, revealed a connection that was always there, waiting to be found. There is a particular quality to the way Euler worked that deserves to be named and understood, because it is a quality that separates the very greatest mathematicians from merely excellent ones. It is the quality of productive boldness, the willingness to make moves that are not fully justified by the existing theory, on the grounds that the result points toward truth and that the rigorous justification will eventually follow. Euler's use of the infinite product representation of sine of x divided by x was not rigorous. He assumed, without proof, that a technique that worked for finite polynomials, factoring them through their roots, could be extended to infinite polynomials. This assumption was plausible and later proved correct, but at the time it was an act of mathematical faith. What justified this faith? Two things. First, the answer was testable. If pi squared over 6 was the correct answer to the Basel series, it would match the numerically computed partial sums to any desired number of decimal places. And it did. This is not a proof. A wrong formula might agree with numerics to many decimal places for small values without being exactly correct, but it is strong evidence. Second, the method generalized. Euler applied the same technique to the sums of reciprocal fourth powers, sixth powers, and beyond, and in each case got an answer that was both numerically correct and internally consistent with the pattern for even powers. A method that works in one case might be lucky. A method that works in many related cases is almost certainly correct. This combination, testable answers, consistent generalizations, strong numerical evidence, was enough for Euler to proceed with confidence, and he was right. The rigorous justification came later, from the theory of entire functions developed in the 19th century, but it confirmed exactly what Euler's bold reasoning had predicted. The lesson for mathematics, and perhaps for all intellectual endeavor, is that boldness is not the enemy of rigor, it is often the precursor to it. You find the result by being bold, by following your intuition past the boundary of what can be strictly justified. Then you go back and build the justification. The result leads the proof. The proof does not always come first. Euler was perhaps the greatest practitioner of this approach in mathematical history, and the Basel problem solution is its finest example. He did not know, in 1735, that Weierstrass would eventually prove a theorem justifying exactly the step he had taken. He did not need to know this. He knew the step was correct because the answer was beautiful and the numerics confirmed it. The proof would come, as it always does, in the fullness of time. The Basel problem, and Euler's solution of it, occupies a special place in the history of mathematics, not just because it is beautiful, though it is, but because it sits at the junction of so many things. The history of infinite series, stretching from the harmonic series and the triangular reciprocals through the Bernoullis to Euler. The theory of the sine function and the Taylor series, tools developed in the calculus revolution and used here for a new purpose. The Riemann zeta function, which generalizes the Basel series and connects it to the deepest questions about prime numbers. The Riemann hypothesis, which remains unsolved, and which is in some sense the continuation of the investigation that Euler began when he first asked what the Basel series summed to. Standing at the Basel problem, you can look backward and see the entire tradition of mathematics with series and limits that stretches to Archimedes and Euclid. You can look sideways and see the connections to trigonometry, to complex analysis, to the geometry of circles and spheres. And you can look forward and see the vast program of analytic number theory that developed in the 19th and 20th centuries, still active today, still working on questions that Euler's solution raised. The solution is not an end, it is a window. Through it, you can see the landscape of mathematical truth extending in every direction, the nearest features visible and beautiful, the more distant ones still mysterious and waiting. Among those distant mysteries is the question of the odd zeta values, zeta at 3, 5, 7, and beyond. Appert proved in 1978 that zeta at 3 is irrational, a heroic achievement that required methods far more sophisticated than anything available in Euler's time. But no closed form is known for zeta at 3. No representation in terms of pi or logarithms or any other familiar constant. The number just sits there, approximately 1.202, known to be irrational, known to be the value of an infinite sum of elegant simplicity, but not yet connected to anything else in the mathematical universe. Perhaps it never will be. Perhaps the odd zeta values are genuinely new constants, not reducible to anything previously known, representing a level of mathematical complexity that the even values, with their beautiful pi-based expressions, do not. Or perhaps someone someday will find the key, the connection, the function, the identity that reveals what zeta at 3 really is and why it has the value it does. If that discovery comes, it will be because someone did what Euler did in 1735. They will sit with a problem that has defeated the best minds for generations, follow their intuition past the boundary of what can be strictly justified, and find something unexpected and beautiful waiting on the other side. The Basel problem shows that this kind of discovery is possible, that infinity can be tamed, that the most abstract and apparently unconnected areas of mathematics can turn out to be deeply related, that pi can be hiding in a sum of fractions, waiting for the right person to look. As the very last thought before the story closes completely, consider the young Gauss with whom the story began. The legend of Gauss pairing numbers in his classroom, recognizing that 1 and 100 sum to 101, as do 2 and 99, as do all pairs from the ends, is a story about seeing structure where others see only labor. The teacher expected tedious sequential addition. Gauss saw a pattern that made the calculation immediate. This is the mathematical impulse at its most fundamental, the impulse to find the shortcut, to see the structure beneath the surface, to replace effort with insight. It is the impulse that drove Orsmy to group the terms of the harmonic series in a way that revealed its divergence. It is the impulse that led Leibniz to rewrite the triangular number series in a form that made it telescope. It is the impulse that led Euler to connect the Basel series to the sine function through the infinite product, to see, where others saw only a stubborn numerical mystery, a deeper structure that made the answer inevitable. Mathematics, at its best, is the systematic pursuit of this impulse. The search for the pattern beneath the surface, the structure beneath the chaos, the simple truth beneath the apparent complexity. The Basel Problem is one of the most beautiful examples in mathematical history of this pursuit succeeding, of a patient, centuries-long search for a pattern ending with the discovery of something not just correct, but astonishing in its elegance and its unexpectedness. Pi squared over 6, hidden in the squares, found by a young genius who saw what no one before him had seen. And now tonight known to you, carried in your awareness for a few hours in the dark, and perhaps remembered tomorrow, and perhaps remembered always, as one of the most beautiful truths in the universe of numbers. Rest now. The mathematics will keep. The Basel series sums to pi squared over 6, and will do so forever, patiently, in the darkness, whether anyone is listening or not. And that is the most peaceful thought in the world. As we come to the end of our journey tonight, the story can begin to settle around you. We have traveled from the schoolroom legend of young Gauss to the 14th century genius of Orsmy, from the rivalry of the Bernoulli brothers to the triumph of Euler, from the harmonic series that refuses to converge to the reciprocal squares that converge to pi. We have touched the Taylor series and the sine function and the infinite product and the Riemann zeta function. We have stood at the edge of the great unsolved problem of the Riemann hypothesis and looked out at the territory beyond. There is no need to hold any of that tightly now. You can let the details soften into impressions. The image of fractions getting smaller and smaller, their sum approaching a fixed number from below. The image of a sine wave oscillating through zero at every multiple of pi. The image of Euler writing, quite unexpectedly, I have found an elegant formula depending on pi. The image of pi squared over 6, clean and exact and eternal. Let these images dissolve into the background of your awareness, like candle smoke rising and disappearing into the dark. The universe of numbers is infinite, and its beauty is inexhaustible, and tonight you have spent a few hours in its company. The sum of the reciprocals of the squares is pi squared over 6. The odd zeta values are mysterious. The primes are distributed according to a law that the zeros of the zeta function know but have not fully told us. And somewhere in that enormous, ancient, patient mathematical landscape, the next great discovery is waiting for the next great mind to find it. Let your breathing slow. Let your body settle into wherever it is. The universe will keep unfolding on its own, just as it always has, steady, patient, and kind. Sleep well. Good night. Still drifting. Let the rain take over from here. Close your eyes and let it wash everything away.